Okay, we are recording. We are continuing our section 13.7 Stokes theorem, and we are looking at examples. We did one example already, and here's another nice example. Let me give you to copy this example down. Now, this example is not in the textbook, but this is an example I'm selecting just to give you additional examples. Let me give you a moment to copy this example down, and we will proceed. Okay, so let's see here what this problem's about. We want to use Stokes' theorem to evaluate. Now notice here, we're evaluating this flux integral, where the vector field F, the vector field is the curl of the vector field. That's your vector field. This is a flux integral, and we're going to use Stokes' theorem to compute the flux integral. So Stokes' theorem, remember, well, I want to say it the right way. Yeah, okay, that's fine. Let's just keep it simple. What's our surface? We have to have a surface for Stokes' theorem. The surface is the part of the cone that lies between the planes y equals 0 and y equals 3, oriented in the direction of the positive y-axis. Okay, so this means that the normal vectors are protruding in the direction of the positive y-axis. Okay. And the cone, of course, the cone, if, the cone would be y equals plus the square root of x squared plus z squared, because we're looking in the positive y-axis. So the cone, right, a cone that is y squared equals x squared plus z squared would be a cone that goes along the y-axis, right? It would be a cone that goes along the y-axis. So it's a sideways cone. And the y-axis Well, I'll draw it in green here. That's the y-axis. But it's just going to be, well, I want to be careful here. Hold on. The plane y equals 0 and y equals 3, the plane y equals 0 is the xc plane. The plane y equals 3 is 3 units to the right of that. So it's going to be just this part of the cone, just this part. And it ends at y equals 3. So, okay, let's get a little bit better picture here. So, okay, there's the formula sheet that you'll have access to. Let's get to the picture. Here we go. This is the picture. Okay, so, all right. I want to be a little careful how I discuss this problem with you. So the surface S is the cone surface, and it stops at y equals 3. So if you, we'll just phrase it the right way. If you think of y equals 3, that plane, that vertical plane cutting through the cone, the cut is going to be right here. I'm highlighting it in red. That's the cut. And the orientation is in the direction of the positive y-axis, which means that the normal vectors point in the direction of the positive y-axis. So we have to think of ourselves, in this orientation, and I've written some words here. As you walk along the closed curve C in the direction shown, and the direction is, this direction here. As you walk along that direction, your head points in the direction of the normal vectors. Okay, your head is pointing upward. Well, no, it's pointing like, if you stand on that, if you walk around that closed curve C, okay, like you're walking like, like pretend you have, I don't know, magnetic boots or something, and you're walking around that curve. Your head's pointing in the direction of the normal vector, and the cone S is on your left. If the surface S is like, it's like a, it's to your left, but it's inward, it's like a pit. So the surface S is to your left, it's just below you as you walk around that curve C. And that's the situation that we're dealing with here. That C has positive orientation if you walk in the direction where the, shown in the picture along C, if you walk in that direction. Please let me know if you have any questions. I would consider this problem to be one of the harder problems, which is why I want to do one with you. so that you're, prepared when you do these homework problems. So I'm letting you copy the picture and the words. Again, please let me know if you have any questions. All right, well now, what we have to do, okay, is remember what we're trying to find here. I want to say this the right way. Let me see, maybe I can put this over here. So Stokes' theorem, okay, we're looking to find this surface integral. And by Stokes' theorem, that equals the integral. Well, it equals this line integral, which is work. Okay, that's what we need to find. We need to find this. So the idea is that this here, if we were to try to find that flux integral, work it out by hand, it would be difficult. We're going to use Stokes' theorem to find it by simply finding the work that the vector field does in moving a particle once along this path here, that red path, that space curve. So we're going to need to be able to figure out, what is R of t here? What is R of t? Okay, because to compute this work integral here, we need to know, well, I want to be careful. We're going to need to find, if we're going to use the regular definition of the work integral, we're going to need to find that vector function R of t. So I'm not going to, let's assume that, well, that's what I'm going to find. So I'm not worried about using the fundamental theorem of line integrals. I'm not saying that that vector field F is a conservative vector field. I would have to test it. It looks pretty messy. So I'm just going to proceed on here. So, okay, so here's the question. we know that we want to find this integral. For the space curve, as I drew it on the picture, which parameterization goes with the positive orientation? So you notice you have two choices. You have like choice 1. Now, y is equal to 3, but to get the rotation in terms of the xz plane, x could be 3 cosine of t, y could be 3 sine of t. A second choice would be to let x be, y equals 3. X is 3 sine of t, and z is 3 cosine of t. Only one of these is going to work. So the reason I'm doing this is I'm thinking, well, when students do this kind of problem and they parameterize, they want to find the vector function that traces out that space curve, some students are going to have 3 cosine of t, 3 sine of t for x and z. Other students are going to have 3 sine of t for x and 3 cosine of t for z, but only one's right. So what I do is on the next page, don't worry about the 3. Okay, worry about the x and z components. Worry about those components. Let's draw 2 space curves, one for the parameterization 1 and one for parameterization 2. That's what I do on the next page here. Okay, so I'm not worried about y equals 3. Okay, I'm just worried about the x and z components. So if x is 3 cosine t and z is 3 sine of t, in terms of the xc plane, although remember this space curve is located 3 units to the right of the xc plane, this would be the orientation that you would be doing. I mean, this would be the space curve. Of course, it's a circle with radius 3. And it would be going in this direction. Starting at t equals 0, it would start at that point, 3, 0. And then, it would go like this. On the other hand, if x were 3 sine of t and z were 3 cosine of t, when you start at t equals 0, you'd be starting at the point 0, 0, 3. And as t increases, you'd be moving in this direction. So if t is pi over 2, you would be at 3, 0. Right? So you have, I've drawn both space curves here. Which one is right? Well, if we go back to the picture, and look at the red space curve, we see, like in the want to say it the right way. One moment. One moment, class, one moment. If we think of like 0, 3 as being like right here, okay, the highest point on that space curve, which would be, I'm sorry, it would be 0, 3, 3, right? That would be the point. I'll label it. That would be the point 0, 3, because y is 3, 3. And the space curve is moving in the positive x direction. It's moving in the positive x direction. Again, at 0, 3, 3, that goes, right? Now, hold on, I'm just kind of, yeah. And then this curve moves in the positive x direction. So of the two space curves that I drew, okay, which one starts from the high point? So I think, if you think about the high points, here are, hold on here. Here are the high points, right, where z is 3. It's the second space curve with this parameterization, where x is 3 cosine, where x is 3 sine t, y is 3, and z is 3 cosine t. It's the second space curve that from the high point, it moves in the positive x direction, the space curve. And that's the parameterization you're going to use for r of t. Like I said, this problem is, I would consider to be probably a hard problem to do, a hard one, but that's why I'm doing it with you, so that you're, so that you've seen a hard one done. If you're comfortable with this kind of problem, then the homework problems should be, hopefully, you should be comfortable with those. Are there any questions before I go to the next page? Please let me know if you have any questions. Grayson, how are you feeling with this? Okay. I've called Grayson before. Matthew, how about you? Are you okay with this? Do you have any questions? Man, I hope there's some people here. I'm getting worried. Yeah, sure. Sure. Back to the last page. Sure. Okay, this one here. All right, Simon. So there's always students who I call, like I called Grayson, for instance, in previous class. He didn't answer. It just happens, class. I'm sorry about it. Some students are logged in, but they're not here. But let's just proceed forward here. Now, Matthew, you're usually here when I call your name. Okay, you go back to the picture. Ashi, how about you? Are you all right? Okay, no problem. No problem, Simon. Man, I'm getting worried. I'm calling. Okay, good. Thank you, Ashi. Ooh, I want to be sure at least half of you are here. All right. Okay, well, Samuel, that's a possibility. Samuel, that is a possibility. Samuel, did I answer your email question adequately during the break, by the way? I know you had that question. I think I emailed you, right? And I think, okay, so I think that's fine. Wonderful, wonderful. Okay, so now are there any questions before I proceed on to before we proceed on? Okay, wonderful, Norina, very good, and Simon's good too. Okay, so this is the orientation we're going to use, and we have to use that one, or we won't get the right answer, class. We have to use that one. So now it's just a matter of working it out, and this one there's quite a bit to work out. We find the derivative of r with respect to t, and now we know what x, y, and z are, and I'm going to plug them in, x, y, and z in for the components x, y, and z. Hold on, nope, wait, that's not right. That's not right. Hold on. Whoa. Yes, Abby, that's fine. That's fine. We might be able to even do that during the break. But yes, that's fine. Either way, either way. You're welcome. No, the x, y, and z is here, right? This is the x. This is the y. This is the z. It's from R T. So x, y, and z go here, here, and here, 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 and here, and here, here, and here. They get put into the vector field. The vector field, the vectors are functions of position, but what gives the position on the space curve? What gives the positions? It's R of t. So this, as it turns out, is going to be f of the vector field evaluated at R of t. And now, on the right here, on the right, this is my integral. This is my work integral. And that we need to find. I mean, you're basically now, you know, we're near the end of multivariable calculus. So of course the problems are going to be interesting. We'll call them interesting. So we have to take the dot product right? We have to take that dot product, and then we have to, we're going to have to integrate what we get. Now notice that because of the 0 here, this ugly term here, when we do the dot product, is not going to be involved. That would be an ugly thing to deal with. The sine of 27 sine t cosine t. So we're taking 729 sine squared of t cosine t, multiplying that by 3 cosine of t. That'll give us 2,187 sine squared of t cosine squared of t. And we're going to take 27 sine of t cosine of t and multiply that in the dot product by -3 times the sine of t. That'll give us negative 81 sine squared of t cosine of t. So what we'll get on the next page then is this here. So what I do is I take this integral and break it up into the difference of two integrals. Why not? Makes our life a little easier. And for the first integral, we have this sine squared of t times cosine squared of t. That can be written as sine t cosine t squared. And it's advantageous to do that because this is an identity that hopefully you have seen. How many remember that the sine of 2t is equal to 2 times the cosine of t? Well, no, hold on. I mean, it's fine, but let me rewrite it. The sine of 2 times t is that there's an identity. The sine of 2t is equal to 2 times the sine of t cosine of t. How many remember maybe that from their trig days? I bet Lexi remembers that. She said she had a pretty her instructor drilled her pretty hard on those trig identities, right? So how many recall that identity? All right, Lexi definitely remembers that one. And so, you know, sometimes you just have to remember these problems where you have trig functions. If you just you know, stick to certain ideas, they work out. And the sine of t cosine t, therefore, is sine of 2t over 2. Now, notice I brought the constants out in front of those integrals. And sine squared of t cosine of t, I'm going to let u equal the sine of t, then du is cosine t dt. So that second integral, it becomes an integral with respect to u, an integral of u squared du. But look at this, it's really cool. The 0, where's that come from? Well, that's, you know, the sine of 2 pi. 2 pi was the top t limit. So the sine of 2 pi is the corresponding u limit. That equals 0. And then 0 was the bottom t limit. Well, the sine of 0 is just 0. So we get an integral that equals 0. If your limits, beginning and ending limits on your definite integral are equal, then you have no area, right, underneath the curve. So yeah. the sine squared of 2t. So, you know, the 2 squared, I bring it out as 4. Sine squared of 2t is, so again, another identity. If you remember, I don't know if you remember this one, that the sine of sine squared of theta is equal to 1 minus cosine of 2 theta all over 2. And so theta equals 2t. And, you know, you get down to here. So this kind of integration, sometimes I'm trying to show it to you here, just so that you know, see it, and it won't be uncomfortable for you. Grayson, what do you think of this? Are you good with this? All right, Christopher, how about you? Are you good with this? Oh my goodness, I hope people are here. Norina, are you comfortable with this? You're good, all right. Simon, how about you? Are you okay with this? Okay, all right. All right, well now what we have to do is we have to get the antiderivative. And that's not hard. This is really a calculus 2 problem. So the antiderivative of a half is a half t, and the antiderivative of cosine of 4 of t is sine of 4 of t over 4. So we get then, you have to multiply that, of course, by the half on the bottom. You get 2,187 over 4 times, well, you get this expression here. And you just substitute in 2 pi and 0 where they go. So you get the sine of 8 pi. We know that's 0. I mean, basically, this is going to equal 0, right? Sine of 4 times 0, that's the sine of 0. So that's going to equal 0. I mean, it's 2,187 over 4 times pi. Then, you know, this term times this term. Absolutely fascinating. Absolutely fascinating kind of problem. So there you use Stokes' theorem to compute that flux integral, which might have been very difficult to do if you were to try to compute this flux integral directly, you know, it might have been impossible to do, but Stokes' theorem made it manageable. Are there any questions on this problem? This problem and the last problem we've covered section 13.7 quite well. Are there any questions? Okay, I will stop the recording then. Very good.